We have a nice theorem. Orthogonal sets are linearly independent. If S includes vector v1, v2, v3, vn is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. Well, how do we show independency between vectors? So if you form the linear combination equal to 0, you need to show that it only has trivial solution. But take a look. If you find the inner product between the linear combination of these vectors and any other vector in this set vi, it is equal to, well, this combination is equal to 0. So wherever you see this combination, just set it equal to 0, comma vi. So here you have C1 and the inner product between V1 and Vi plus C2, inner product between V2 and Vi plus Ci, the inner product between Vi and Vi plus the rest of the terms, and Cn times the inner product of Vn and Vi. On the right-hand side, it must be equal to 0 because you have inner product between 0 vector and any vector which must be 0. S is orthogonal. So Vi and Vj, their inner product is equal to 0 for any indices like I and j that are not equal to each other. So what's the meaning of that? It means that Ci times the inner product between Vi and Vi is equal to 0. And then if you write it down as the magnitude of Vi to the second power, it cannot be equal to 0. Very good. This means that every Ci must be 0 and the set must be linearly independent. So basically, since we know that the inner product between Vi and Vi, which is equal to the magnitude of Vi to the second power, is non-zero, it means that there is no other choice but Ci be 0. So we just showed that this equation equal to 0 has only trivial solution. Another theorem for you. If V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors form a basis for vector space V. One example for you, show that the set S is a basis for the space of dimension 4. So S includes V1, V2, V3, and V4. Well, this set has 4 non-zero vectors. If you find the dot product between V1 and V2, 2 times 1, 3 times 0, 2 times 0, negative 2 times 1 becomes 0. V1 and V3, the dot product between these two, 2 and negative 1, 3 and 0, 2 and 2, negative 2 and 1. It is also 0. V1 and V4, 2 and negative 1, 3 and 2, 2 and negative 1, negative 2 and 1 is also 0. V2 and V3 become 0 as well. V2 dot V4 is also 0. What's the meaning of that? It means that you have a set of orthogonal vectors. They are 2 by 2 perpendicular or orthogonal to each other. So what's the meaning of that? It means that since you have an orthogonal set of non-zero vectors, it forms a basis for V. So all you needed to do was to check that they are orthogonal to each other as well. So please note that when you have dimension n, you have exactly the same number of vectors. So if it's dimension 2, you must have 2 vectors. If the dimension is 3, you must have 3 vectors. If the dimension is 4, you must have 4 vectors. And as long as they are orthogonal to each other, it forms a basis. So it gives us a very nice criteria to check to see if you have a basis or not. Coordinates relative to an orthogonal basis. Suppose B is a collection of vectors v1, v2, and vn. It is an orthonormal basis for an inner product space B. Then the coordinate representation of a vector like W relative to B is W is equal to the inner product of W and V1. Remember that these are all values. These are all numbers, scalars, times V1 plus the next scalar, the inner product of W and V2 times V2 plus the rest of the terms plus the inner product of W and Vn times Vn. So it makes our life much more easier in finding the coordinate representation of a vector relative to a basis. If B is a basis for vector V, there must exist unique scalars like C1, C2, Cn, such that W can be written as a linear combination of Ci, Vi. What's the meaning of that? It means that if I take the inner product with Vi, the inner product of W and Vi is equal to W is linear combination of V1, V2, V3, Vn. So I'm just substituting that just right here. And then this is equal to C1, the inner product between V1 and Vi, plus C2, inner product V2, Vi, and Cn, inner product Vn and Vi. But we know that since B includes orthogonal vectors, this equation is basically written as Ci, the inner product Vi and Vi, because all of these become zero. The only non-zero quantity is Ci, the inner product between Vi and Vi. So what's the meaning of that? Since B is orthonormal, it means that each vector is a unit vector. So the inner product between Vi and Vi, which is equal to the magnitude of Vi to the second power, must be equal to 1. And it follows that the inner product between W and Vi is equal to Ci times 1, or just Ci, as you see right here. Gram-Schmidt has a nice process that helps us to convert vectors into nicer format. What do I mean by that? Take a look. If B is a set of vector like V1, V2, Vn, is a basis for an inner product space B, and B prime includes W1, W2, Wn, where W1 is equal to V1, W2 is equal to V2 minus this scalar, this number multiplied by V1, which is the inner product between V2 and W1, divided by the inner product between W1 and W1 in the direction of W1. And W3 is equal to V3 minus, we have more algebra to include everybody, the scalar in the direction of W1 minus another scalar in the direction of W2. You can continue this process. Wn, which is Vn minus the rest of these subtractions, then for sure you can say that B prime is an orthogonal basis for V. So this nice theorem says, hey, guys, give me any sets of vector which is a basis for an inner product space V. I can take this set and give you an orthogonal basis for V. And finally, if Wi is equal to, if Ui is Wi divided by the magnitude of Wi, it means that we are normalizing Wi's, then U1, U2, U3, Un is an orthonormal basis for V. It means that they are orthogonal and they are unit vectors. For sure, you can say that v1, v2, v3, vk span v, which is the same as saying that, hey, u1, u2, u3, uk span v as well. I know there are a lot of algebra involved, but this is a nice method. It guarantees you can convert any basis into an orthonormal basis. For example, suppose I give you two vectors like v1 and v2. This is the basis for the plane. Now, how do we apply Gram-Schmidt method? In this method, remember that w1 and v1 are the same. We don't change the very first vector, but the second vector, w2, is v2 minus. Now the inner product in this vector space is the dot product. v2 times v2 dot w1 divided by w1 dot w1. And this is just a scalar. This is just a number multiplied by vector w1, which is just v1. Very good. v2 is 0 and 1 minus a half times 1 and 1. So again, the dot product between v2 and v1, here w1 and v1 are the same. 1 times 0 is 0, 1 times 1 is 1. That's how you end up with 1 on the numerator. On the denominator, it is just the dot product between 1 and 1 by itself, which is 1 plus 1 or 2. Now, if you do the algebra, we get negative a half and a half. So we found two vectors, w1 and w2, that forms an orthogonal basis for the plane. So if I ask you to find an orthogonal basis for the plane, this is the process that you're going to take. But if I ask you to find an orthonormal basis, you have to go to the next stop. You need to normalize each vector as well. u1 is w1 divided by the magnitude of w1, which is 1 over square root of 2, times 1 and 1, which is square root of 2 divided by 2, and square root of 2 divided by 2. And u2, you just normalize w2. You found w2 here. You're going to divide that by the magnitude of this vector. It is 1 over square root of 2 multiplied by negative a half and half. You can just switch this. You get square root of 2 times negative a half and a half, or negative square root of 2 over 2 and square root of 2 over 2. So that's how you find an orthogonal basis and orthonormal basis. These two vectors, both of these two vectors are unit vectors and form a basis for the plane itself. So when you're writing R2, it is your plane. And again, the inner product function is the dot product in this world. The last example for you, apply Gram-Schmidt orthogonalization method and also orthonormalization method to the basis B, which includes 1, x, and x squared in the vector space of all polynomials of degree 2 and less. And then it says, hey, for this vector space, I want you to use this inner product function. This inner product function says, hey, use the definite integral between the multiplication between P and Q. Let us begin, everybody. Here we go. The very first vector is 1. The second vector is x. The third vector is x squared. As you remember the process, w1 and v1 are the same, so it is going to be constant function 1. w2 is v2 minus the scalar multiplied by vector w1, which is v1, 1. So here you have v2, which is x, substitute that here, minus. Here, if you find the inner product between v2 and w1, this is basically calculating the definite integral of -1 to 1 of v2, which is x, times v1 and w1 are the same, so it is 1 times dx. But here you have an odd function over symmetric domain. It is equal to 0 for sure. So that's how you end up with 0 here. So you get 0 divided by 2 times 1, which is x. So this is your W2. Now let us move on to calculate W3, which is V3 minus the scalar times W1 minus the scalar times W2. So here you have V3, which is x squared. So x squared is just right here, minus 2/3 divided by 2 times 1. Again, these are just basically finding the definite integral. So here, if I ask you to find the definite integral between these two functions, between W3, between V3 and W1, V3 is x squared, and here you have your W1, which is 1, so it doesn't change this function, dx. This is equal to 1/4 x to the 4 between -1 and 1, which is equal to basically 0. And let's see. And here you have W2. You can continue this process, everybody. Just calculate each one of these inner product. Here you have, for example, W2 and W2. Well, W2 is x, so x times x. So this guy becomes a third x cubed. Then you have 2 divided by 3 and so on. So you can continue this process, everybody, and do the calculation, and you get this third function, which is x squared minus a third. And it basically gives you orthogonal functions, orthogonal vectors, W1, W2, W3, but you can normalize each one of them by dividing each by its magnitude. So U1 becomes W1 divided by magnitude of W1, U2 is W2 divided by magnitude of W2, and so on. So we found 3 functions, 3 polynomials that form a basis for the vector space of all polynomials of degree 2 or less.